Hey everyone, my name is Julia. I'm a product manager on the C++ team at Microsoft. My team maintains a suite of developer tools for C++, including the MSVC compiler toolset, MS Build, VC Package, Visual Studio, and VS Code. I specifically work on the C++ development experiences in VS Code, and today I'm going to give you the tips and tools to level up your debugging workflow. I have 4 key recommendations for optimizing your debug experience. The first 2 are specific to C++ programs, but the second 2 are applicable to all types of applications. The first recommendation is to use CMake Presets to easily debug the same project on different platforms and in different editors and IDEs. The second recommendation is to use Disassembly View when you're debugging to understand how data is represented in memory. The third recommendation is to automatically catch bugs in your program before shipping to production by setting up a CI/CD pipeline to ensure you're only shipping the highest quality products. The fourth recommendation is to use GitHub Codespaces to create consistent, fast, and clean development environments accessible from your browser. To understand how all these recommendations come together, let's look at the high-level lifecycle of an application. So here's the high-level lifecycle of an application, right? You write your code, you build, test, and debug your program locally. Then you send it off to your continuous integration, continuous deployment pipeline, merge it into source, and repeat. Let's break this down into 2 high-level categories, things you typically do locally and things that happen in the cloud. Raise your hand if this workflow sounds familiar. How many of you are pulling source code down onto your local machine, editing, building, and debugging locally, and then sending your code off into a continuous integration pipeline in the cloud where it's tested and merged into source? Raise your hand if that's you. So developing locally has its benefits. You're used to the look and feel of your machine, you have your editor or IDE configured exactly to your personal preferences. I know how important picking the right color theme is when you're coding, but debugging locally also has its challenges. Let's talk about them. What are some common problems faced by your team when it comes to building and debugging locally? Please feel free to write some answers in the chat. From talking to customers, these are the common pain points that I hear about. The first is that you and your coworkers are on different host operating systems, so it's difficult to share your build and debug configurations with each other. Maybe you have to build, test, and debug your program on different platforms. And each time you switch platforms, you have to spend time getting your program to build successfully because dependencies aren't set up correctly and the build and debug configurations are different since you're on a different platform. Or maybe you and your coworkers are using IDE-specific build and debug configurations, like Visual Studio-specific build and debug configurations. And that makes it difficult to switch between different editors and IDEs. And if you're switching platforms, you might need to switch different editors or IDEs if one platform doesn't work on another, if one IDE doesn't work on another platform. These pain points are real. What happens when you can build your project on your Windows laptop in Visual Studio, but your coworker can't build the same program on Mac OS with VS Code because their build system and their libraries aren't configured correctly? Debugging toolchain configuration issues is not fun. So how do we avoid that? How do we ensure that switching environments or editors won't break your build? Now picture this. There's a JSON file that lives at the root of your project folder. In this JSON file, you define configure, build, and test options for your project. And you can define them for as many platforms as you'd like. This file is checked into source, so it's easy to share with teammates. And you can use this file to drive builds from the command line and in various editors and IDEs, even in a CI pipeline. And because you have options defined for all the different platforms your program targets, you can use the same file when you switch operating systems or architectures. This beautiful vision exists. It's called CMake Presets. And it's our first recommendation for leveling up your debugging workflow. Some other tools you can use to solve your cross-platform debug problems and prevent them from ever happening again include VC Package, Visual Studio, VS Code, and GitHub Actions and GitHub Codespaces. I'll dive into each of these tools today, but let's start with CMake Presets. So our first recommendation is to use CMake Presets to easily debug the same project on different platforms and in different editors or IDEs. How does that even work? Well, let's start with an overview of CMake. What's CMake? CMake is an extensible open source system that manages the C++ application build process in an operating system independent and compiler independent manner. Unlike many cross-platform systems, CMake is designed to be used in conjunction with the native build environment. You put a script called cmakelists.txt in your project directory, which CMake then uses to generate standard build files, like make files if you're on a Unix system. Basically, CMake generates a native build environment that will compile source code, create libraries, generate wrappers, and build executables in arbitrary combinations. Can I get a show of hands for people who are currently using CMake? I'm raising my hand with you. Now, keep your hand up if you're using CMake Presets. I can't see you right now, but I bet a lot of money that most of you put your hand down. CMake Presets are pretty new, and I know how unappealing changing your build process is if you already have one that's working, but CMake Presets will make your life so much easier. You'll see in my demos. So what even are CMake Presets? I've talked a lot about how great they are, but I haven't told you yet what they do. Well, one problem that CMake users often face is sharing settings with other people for common ways to configure a project. CMake Presets solves that problem. In CMake 3.19, CMake added support for a file called CMake Presets.json, which allows users to specify common configure options and share them with others. For CMake 3.20, our team at Microsoft worked closely with Kitware to add support for build and test presets. So initially there were configure presets, now there are also build and test presets. So as of CMake 3.20, CMake Presets.json supports 3 types of presets: configure, build, and test, and the most recent version of this file, v3, which is what I'm using in today's demos, requires CMake 3.21 or higher. CMake Presets lives at the root of a project and is intended to be checked into source control. But if you need to save your own local builds, you can use a CMake user presets.json file, which should not be checked into source control. You can use CMake presets.json and CMake user presets.json to drive CMake in Visual Studio Code, in a continuous integration pipeline, and from the command line, and in any other editor or IDE that enables integration with CMake presets. Let that sink in. One file that you can use to drive CMake builds from Visual Studio, from VS Code, from the command line, in your CI pipeline, and potentially any other editor or IDE. This file is supported by Kitware. It's not just a Microsoft thing. And you can save as many configure, build, and test presets as you'd like in CMake presets.json. In the Fibonacci project that I'll be using in my first demo, I have presets for each platform that I'd like to build the program on. One for Mac, one for Linux, and one for Windows. Let me show you what they look like. Each configure preset has a unique name, which is what you'd use when passing the preset to CMake on the command line. Now, all this preset does, if you look at it, is set the CMake build type to debug and the compiler to Clang++. How can CMake build my program, which has project dependencies, includes third-party libraries, with just this minimal information? Well, you can also see that it's inheriting a base preset. Presets support inheritance. It's common that you'd have a hidden base configure preset that sets things like the generator, the architecture, and environment variables. Then other configure presets inherit and override the base configuration properties. Here's my project's base configure preset. The majority of these fields map to options you would pass to CMake when invoking CMake from the command line. In fact, everything that impacts the CMake command line can be captured in configure presets, build presets, and test presets. For example, setting the generator property is the same as passing --g to CMake on the command line. You could set the architecture property, which would be the same as passing -a to the command line. Finally, I'm setting a few CMake variables with the cache variables object. Everything in this object is the same as passing a variable with -d on the command line. Cache variables and environment variables are inherited through the inheritance field, and the presets variables will be the union of its own variables and the variables from all its parents. If multiple presets in this union define the same variable, the standard rules of inheritance are applied. So the macOS base configure preset that I showed you inherits this base configuration and sets the compiler to Clang++ and the CMake build type variable to debug. Now on to build presets. A single build preset maps to a single --build invocation from the command line. But your CMake presets.json file can contain as many build presets as you'd like. Build presets also support inheritance, so you can define a core build preset and inherit it in other build presets. There's a one-to-many mapping from configure presets to build presets, and the build directory is inferred from that specified configure preset. By default, any environment variables specified in the configure preset will be inherited by the build preset, but you can turn that off if desired. At this point, you might be thinking, oh great, another JSON file for defining CMake options. I want to reiterate that this JSON file greatly reduces complexity and ambiguity because this single file can be checked into source and used in Visual Studio Code, in Visual Studio, from the command line, and in a CI pipeline. In the first demo, we'll use CMake presets to build the same project across 3 different operating systems and 2 different editors and IDEs. So here I have my Fibonacci program opened in Visual Studio, and this is my CMake presets.json file in my project root folder. I have my base configure preset, which sets things like the cache variables and any environment variables, and then I have base configure presets for each of the operating systems and platforms that I'm targeting with this project. So I have my Windows configure preset, which sets the architecture and the compiler and host OS, and I have this for Mac and Linux as well. And then I have my build presets. I have a few build presets, 2 for each target operating system for this project, and test presets, 1 for each operating system, so 1 for Mac, Linux, and Windows. Visual Studio will read from this CMake presets.json file and then display the relevant CMake configure, build, and test presets in these drop-downs at the top of the window. So the very first drop-down shows you which platform you're targeting, and I'm targeting my local machine, which is my Windows Surface Book laptop. And then next to that, I see a drop-down with the configure presets. That's where you see Windows base. And it'll only show you presets in this drop-down that apply to the target platform. That's why I'm only seeing my Windows ones. And then the build presets shown are the ones that are tied to that specified configure preset in the middle drop-down. So To configure this project, select Project and delete cache and reconfigure. At this point, CMake is using the configure and build presets that I selected to configure this program. All right, so the configure was successful and my build files have been written to a build directory. In order to build this project, I would recommend switching to the CMake Targets view in the Solution Explorer. Select the button next to the Home button to switch to the CMake Targets view. And then here I have two CMake targets for my sample Fibonacci program. There's the program executable that outputs the Fibonacci sequence, and then there's one called Fib tests, and those are the unit tests that I've created for this project. So right-click the executable you want to build and select Build. And then we can set a breakpoint and debug. To debug, you can either select the desired target from this drop-down with the play button. So again, I see my VC package example, which is the Fibonacci program, and I'll select that one. And then you can either just click on that Run button, or you can go back to the CMake Targets view and right-click and select Debug, whichever you prefer. So this is launching our debugger in Visual Studio. All right, and in this debug UI, you can see a lot of information about your variables, their values, their types, and we can step through the program to watch the values of those variables change. We can disable the breakpoint and continue running the program, and then we should see the first 15 terms of a Fibonacci sequence printed, which we do in the debug console. You can also test your program using ctest and the test presets defined in your CMake Presets.json file. To do that, select Test at the top of the screen, and then select Run Test Preset for Windows Base. So it's saying Windows Base because that is the preset that I have, the configure preset that I have selected. It's running ctest, and in the output I see that my test passed. Now, the really cool thing about CMake Presets is that if I switch to a different platform or architecture, as long as I have presets for those platforms and architectures in my CMake Presets.json file, I don't need to do anything else. So let's switch from targeting my local machine to targeting a Linux host. So click on that drop down, and if you were to add a new host, you could say Add Connection. But I already did this, and that's the host 40.71. That's the one that I had already connected to. So let's select that from the dropdown. You would also see WSL targets in this dropdown, by the way, not just SSH, but for this demo, I'm using SSH. Now, what is this Julia Linux base preset? That wasn't in my CMake Presets.json file. Well, I actually added a CMake user presets.json file to this project for this Linux build, just to show you how this would work. So basically in my CMake user presets.json file, I have defined a new set of presets, and then Visual Studio is showing me the union of the presets from CMake user presets.json and CMake presets.json. But I'm just going to select the ones from CMake presets.json. Let's go with Linux base. And for build, let's do a clean build. So we'll do project, delete cache, and reconfigure. Exactly the same thing that we did when we were targeting Windows. And if you look in the output, it says copying files to a remote machine. So the remote SSH experience in Visual Studio works differently than it does in VS Code. In Visual Studio, it's copying files from your local machine over, and in VS Code, those source files live on the target host itself. Okay, we had a successful configure. Now I'm going to build the program, which is that VC package example executable. And now let's debug, and this time I'm just going to use this play button. Oh, and I don't have any breakpoints set, so this should just run through. Yep. And there is the program output, and this time it's in the Linux console window. Switching gears a bit, let's go to Visual Studio Code on Mac OS. I just want to show you how to use CMake Presets in VS Code. It's a slightly different UI, but the same idea. So I have my CMake Presets.json file. This is the same file that I was using in Visual Studio on Windows and on Linux. You'll notice that I don't have the CMake user presets.json file. That's because that was a local file and it's not intended to be checked into source. And I'm now on a different machine, so I don't have it anymore. But that's okay. I don't need that to build on Mac OS. I can just use the standard CMake presets.json file. In order to use CMake presets and CMake in general in VS Code, you need to install the CMake Tools extension. You can do that by heading over to the extension marketplace, which is on the left side of the screen, that icon with the 4 squares. And then search for CMake Tools, and it is this one. It's maintained by Microsoft. So I already have it installed, but this is what it looks like for you to go and find it on your own. And the CMake Tools extension contributes these buttons to the blue status bar at the bottom of the screen. These are all coming from CMake Tools. That first one is showing me which configure preset I have selected. So if I just click on that button, I can switch to a different configure preset. And look, it's only showing me my Mac OS configure preset because it knows I'm on Mac OS. So I'll select that. And then there's that build icon, and next to that shows the build preset. So let's do the clean build. And then let's just hit that build icon, and this will reconfigure and build the project. Okay, so we had a successful build. I'm going to set a breakpoint and start a debug session in VS Code. And I can do that using the CMake Tools extension by clicking on that debug button in the blue status bar. And now the debugger has launched, and I can step through here, look at the values of my variables in the debug pane on the left. And I'll disable the breakpoint, continue running the program. And my output appears in the debug console. Now, if you want to just run the program in the terminal, you can click on the play button next to the debug button, and that will just print the Fibonacci sequence output in the terminal instead of in the debug console. In order to run tests using ctests in VS Code, click on the second from the right button, select the test in the status bar, select this test preset, and I'm just showing you here that I have a little subfolder with my unit tests for this Fibonacci program. And then you click on that rightmost button in the status bar with the check mark that says 1 out of 1 test is passing, and I can see more detailed output in the output window. And let me just quickly show you the command line syntax if you wanted to run, if you wanted to use CMake presets to drive builds from the command line. So if you use the --list -presets equals all, then you can see all of the presets that are available to this project, which will be the union of CMake presets.json and CMake user presets.json. And then use the --preset flag and the name of the configure preset that you want to use to configure the project. Great. Now let's build. So we'll use CMake --build and then the presets flag again, and then the name of the build preset that you want to use. And I'm doing Mac OS core build, and that's actually not the name of a preset in my file, so it's yelling at me, but it's telling me what I can do instead. So I'll correct it and use the clean build. And that's building my program. And then to run tests, you use this ctest command instead of CMake. Start with ctest, and then the preset flag, and then the name of the test preset that you want to use. Great, so now I see the test successful output in the terminal. Now, hang on a second. What if my program requires third-party libraries that aren't installed on my new machine? CMake can't magically build successfully without those, right? Wrong. Well, technically, yes, you're right. You need to install those dependencies to build, but if you use CMake and VC package together, VC package will automatically install missing dependencies when you configure and build your project with CMake. So there's an illusion of it working magically. Let me show you what I mean. I have the same project open on Mac OS in Visual Studio Code. And I'm going to delete my build directory because that's where VC package had been installing my third-party dependencies, which I do have for this project. See, I have FMT and CBP iter tools. So let's delete that whole folder. And now I see those include header squiggles at the top of my file. That's because those third-party libraries are no longer installed. So I should be seeing those squiggles. I have my vcpackage.json manifest file in the root of my project. And in this file, this is where I'm declaring my project dependencies. I have CBP iter tools and FMT, which are included in my main .cpp file. And then I have gtest, which I'm using to run tests against my program. And in this configure preset, the base configure preset, that's where I've set my VC package toolchain file path. I added the VC package _root environment variable to my path, and I recommend doing that so that you can just use the environment variable VC package root in your base configure preset and then check that into source and share it with other people in case they have VC package located at a different place on their system. So now when I reconfigure and build my project, notice in the output window it says running VC package install. That's the command that reads from the vcpackage.json manifest file and just automatically installs those libraries plus any dependencies of those libraries. And looking at the output closely, you can see it's using binary caching, which makes this process a lot faster. My configure and build succeeded, and all I did was press one button, and CMake and VC package took care of automatically installing my project dependencies that were defined in my vcpackage.json file. Let's talk about some key takeaways from that first demo. With CMake Presets and VC Package, you can easily build and debug your project on and for multiple platforms. CMake Presets.json enables consistent builds from the command line in a CI/CD pipeline from Visual Studio and in VS Code. VC Package simplifies the process of specifying, acquiring, and maintaining project dependencies. And lastly, you can declare project dependencies in vcpackage.json, the manifest file, and check it into source control to ensure you and your teammates are using the same versions of libraries. I'm excited to tell you about a new experience for acquiring artifacts using VC Package. Artifacts, not just libraries, that's the key difference. An artifact can be thought of as a set of packages required for a working development environment. Things like compilers, linkers, debuggers, build systems, platform SDKs. So with this important change, VC Package can not only download and build your libraries from source, it can also bootstrap the rest of your environment, acquiring pre-built binary dependencies for your projects. VC Package Artifacts is still in preview and currently focused on embedded developers. So if you're an embedded developer, now is a great time to try out VC Package Artifacts and let us know what you think. All the embedded developers in this audience will also be excited about the next recommendation for leveling up your debugging workflow, Disassembly View. Recommendation number 2, use Disassembly View to understand how data is represented in memory. When we shipped Disassembly View in VS Code last year, it had been our top ask on GitHub for a few years. That alone is a testament to how helpful Disassembly View can be. I want to talk a bit about what a Disassembly View is and why it's helpful. To do that, it's important to understand how a C++ program is created. For C++ projects, you start with your source code. This is the C++ code that you write in your .cpp files. Then a compiler turns the source code into machine code. What's happening in that process? Typically, the compiler generates machine code, which is either represented in binary, zeros and ones, or hexadecimal, which is what you see in this screenshot. In some cases, though, the compiler instead creates something called assembly language, and then an assembler turns the assembly language into machine code. Machine code is not readable by humans. Assembly language is easier to understand. This is where disassemblers come into play. A disassembler disassembles the unreadable machine code into assembly language, which is more readable. You might be wondering, why should I care about looking at assembly language? Well, looking at the assembly language helps you understand exactly what your compiler is doing. Sometimes the code generated by your compiler isn't giving you the performance you're looking for. Examining the assembly can give you insight into these issues, giving you a chance to make code changes, modify compiler switches, etc., to get what you need. Disassembly View is also helpful for understanding how your program's data is represented in memory. Now, I'll show you how to see machine code and assembly code in Visual Studio Code while debugging C++ programs. I'll be using a simple embedded development project in this next demo. It's blinking an LED with a Raspberry Pi. This Blink program uses the Wiring Pi library, which comes installed on the Raspberry Pi 4. There are 2 ways to code on a Raspberry Pi with Visual Studio Code. You can either connect your Pi to a display and install and open VS Code directly on the Pi. This works because VS Code and the C++ language server run natively on Raspberry Pi architecture. Or you can install and open VS Code on a laptop and use the remote SSH extension to target the Raspberry Pi from your laptop's local instance of VS Code. I'm going to go with the second approach today and use the remote SSH extension to SSH into the Pi from VS Code on my Windows laptop. Once you install the Remote Development Extension Pack in VS Code, you'll see this Remote Explorer icon on the left. If you open the Remote Explorer, you'll see a list of SSH targets that you've previously connected to. You can add a new target by clicking on the plus button. I'm going to connect to one that's already in my list, which is my Raspberry Pi, and then I can actually connect directly to my Blink program folder, which you see right beneath the IP address. So now I've connected to my Raspberry Pi, and you can tell that you're in the remote window by looking at that bottom left corner, and if there's that green rectangle, that's how you know that you are in your remote target environment. In the extension marketplace, you can see which extensions you have installed on your local machine versus your remote target. Clicking on that cloud icon will just install any extensions you have locally onto the remote target. So here's my blink.cpp file, which blinks an LED 15 times, and the length of each blink is half a second, 500 milliseconds. And here's a familiar file. It's CMake Presets.json. And there's also IntelliSense for CMake Presets.json in both VS Code and Visual Studio. If you hover over properties, you'll get information about what they are. And if you start typing architecture, for example, then you'll see autocomplete. I'm using CMake Presets to build, debug, and test my Blink program the same way I did with my Fibonacci program in the first demo. I have two configure presets for this project, Raspberry Pi Debug and Raspberry Pi Release. Let's select the Debug configure preset. And now I'm going to open the command palette and type delete cache and reconfigure. And just so you know, any of these buttons in the status bar coming from the CMake Tools extension, if you don't like seeing them in the status bar, you can hide them, and they're all available as commands from the command palette. Okay, great. I had a successful configure. So now I'm going to select my build preset, and I'll do the verbose build and then hit that gear build icon. And our build succeeded. So now I'm going to start a debug session. I'll set a breakpoint, but I'm actually going to make it a conditional breakpoint so that we break after the LED blinks 10 times. So when I equals 10. And now if I hit that debug button in the blue status bar, we should see this LED, this red LED, hopefully you can see it well, blink 10 times and then break. There it is, 5, 6, 7, 8, 9, 10. Okay, so now it's done. I'm in my debug session, and let's say I wanted to change the value of this blink rate. So I'm going to change delay time to 1000 milliseconds, which you can do by right-clicking and then pressing set value. So now I'm continuing running the program, and each blink is lasting a full second. It's longer. So now I actually want to debug more than the source code, though, right? That's the whole point of this demo, is to show you Disassembly View, so let's do that. I'm going to remove the conditional breakpoint, and because I just want to break every time I hit this line, and I'm going to restart a debug session. And this time, I'm going to right-click on the source code once the debugger launches and select Open Disassembly View. So let's take a look at what we have in Disassembly View. On the left, we have the memory address, and then we have the machine language instructions displayed as hex, which is that middle column, and as assembly language, which is the rightmost column. And the yellow hollow marker indicates which instruction we're at. And you can step through Disassembly View the same way you would a typical debug session. And I just split the window to look at this Disassembly View and source code side by side, but we actually have a new command. If you open the command palette and type Disassembly View toggle source code inline, you can look at both at the same time within the same window. So I disabled my breakpoint, I'm continuing to run my program, and my LED is blinking. So that's how you use Disassembly View in Visual Studio Code, and the remote SSH extension and the CMake Tools extension. Let's talk about some key takeaways from that second demo. The first is that you should take advantage of Disassembly View to look at how your program is being represented in memory. The second is that VS Code provides full C++ IntelliSense and debug support for Raspberry Pi. So why do we debug in the first place? We debug to find and fix bugs, but bug catching doesn't have to stop there. That brings us to our third recommendation. Recommendation number 3, automatically catch bugs in your program before shipping to production by setting up a CI/CD pipeline. The CI/CD pipeline that I'll be setting up in my demo today uses GitHub Actions. But before diving into that, I want to give a brief summary about what continuous integration is and why it's helpful. Continuous integration is the process of automating the build and testing of code every time a team member commits changes to version control. And it has a ton of benefits. To name a few, it reduces risk because you can detect and locate errors more quickly. You can narrow it down to a specific commit to your repository that's all of a sudden causing tests to fail. Secondly, it ensures quality because the shipped product is always tested first. And finally, it enables you to be more efficient. You can spend more time coding and less time manually testing or running long tests locally and waiting for them to finish before moving on with your next task. So GitHub Actions is a great way to set up the CI/CD pipeline. To help you get started, GitHub Actions generates workflow templates based on the code in your repository. And those workflows run whenever a specified GitHub event occurs, such as when you push changes to your repository. These workflows run on GitHub-hosted virtual machines or self-hosted machines. In my demo today, I'll be using my Raspberry Pi as a self-hosted machine. And those workflows are defined in YAML files in your project's .github/workflows folder. For example, when I created a workflow for my Blink project, GitHub gave me templates for workflows that build and test C++ projects. I chose to use the CMake workflow template. And just so you know, you can do a lot more with actions than build and run unit tests against your code. At CPPCon, Microsoft announced a publicly available GitHub action for the C++ community to run code safety checks on their GitHub repositories. Great customer experience starts with quality, and this action enables you to catch bugs before they get shipped to production. The lowest screenshot shows an example of what the check results look like in your PR, but you can also see all the alerts for your entire repository, not just the code that you updated in the PR. Okay, let's revisit this diagram from earlier in the session. These tests and integrate steps in the cloud, that's where GitHub Actions fits into our application development lifecycle. At this point, we've talked about how to optimize your local debug workflows. We saw how CMake Presets and VC Package enable you to easily build and test the same project in various local environments. But there were a few things we still needed to do to those local environments in order to build and debug successfully. Things I did before recording these demos. I had to install a C++ compiler, I had to install CMake, I had to install VC Package, and I had to clone the GitHub repositories onto my machine. Well, what if you didn't have to worry about setting up that local environment at all? Your source code already lives in the cloud on GitHub, or something like GitHub. Imagine if you could just edit, build, run, and debug your code from your browser. No need to install source code or compilers or project dependencies locally. Welcome to GitHub Codespaces, our fourth and final recommendation for today. Recommendation number 4, use GitHub Codespaces to create consistent, fast, and clean development environments accessible from your browser. GitHub Codespaces is a cloud-based development environment for VS Code. You can think of it as Visual Studio Code backed by high-performance VMs that start in seconds. Codespaces provides full development environments with up to 32 cores that can be accessed from a web browser. You can also access them from Visual Studio Desktop or using SSH. From the web, you have access to all the C++ extension and the CMake Tools extensions have to offer, from IntelliSense and code navigation to building and debugging. And because all you need is a web browser, you can debug from any device that has a web browser, like an iPad or a Tesla, although I don't endorse debugging while driving. With GitHub Actions and GitHub Codespaces, you can achieve a fully cloud-based development workflow. Now, I want to call out that you don't have to use GitHub Actions and GitHub Codespaces together. You can pick and choose which parts of your development workflow you want in the cloud. A hybrid cloud local development workflow is very popular. Let's dive into the third and final demo, where we use GitHub Codespaces to code from our browser and GitHub Actions to build and test our program in a CI/CD pipeline. Here I have my Blink project repository open on GitHub. And oh look, there's an open pull request on this repo. Let's take a look at that. Someone wants to change the blink rate from 100 milliseconds to 1,000 milliseconds. Now, I agree that 100 is too short, but I think 1,000 is too long. So I'm going to edit this PR to make it 500. Now, even with minor changes to simple projects, I prefer to make edits in my editor as opposed to the PR UI because I like to see the changes in the context of the whole project. I like having IntelliSense to make sure I'm not making typos, but switching from my browser to my editor and making sure my local repository has the latest changes and resolving merge conflicts takes away from my productivity. It disrupts my flow. Well, here's a neat trick. Open any repository on GitHub and press the dot or period key on your keyboard. I'm now opening my project in github.dev, which is a serverless version of VS Code. Everything is running in the browser. It's free, it's lightweight, it's great for reading code and making quick edits. And you can access it on any device that runs a browser. If you're on a device like an iPad, where hitting the dot key isn't necessarily easy, you can instead replace github.com with github.dev in your repository's URL. If you make changes in github.dev, you can commit them directly to your branch. No push necessary. So I'm going to change this delay time variable from 1,000 to 500. And then in the source control pane, I'll stage my changes, write a commit message, and commit the changes. That's all you need to do. You can also create and switch branches easily by clicking on the branch name in the bottom left-hand corner. If I switch to a new branch, any uncommitted changes stay on the previous branch, giving you neat, isolated working directories that you can return to at any time. So this PR updates the delay time variable from 1,000 to 500 milliseconds. Now, this is a simple project and it's pretty easy for me to find all instances of the delay time variable, but you can imagine with a larger project, it would be helpful to do a find all references to make sure you know all the instances that this delay time variable is being used. That way you can make sure the change from 1,000 to 500 milliseconds makes sense in all those cases. Now, because github.dev is serverless VS Code, not all of VS Code's desktop functionality is available. There are some extensions, like the Python extension that can run in the browser, but the C++ extension is not currently supported here. So to do a find all references before merging this PR, I have two options. I can open the workspace and PR locally in VS Code Desktop, or I can open it in a code space to stay in the browser. Whether you choose a code space or VS Code Desktop, you're brought into the same PR so you don't lose any context. I'm choosing a code space. A code space is a Linux-based container. We often refer to this as the kitchen sink because it contains a bunch of different tools and software like Python, Java, .NET, GCC, GDB. It's a great way to get up and running quickly, and you can customize it further with the dev container so that one, you don't have to reinstall tools in every code space, which would happen if you installed them through the terminal. And two, you can share this config file with teammates and use it in any VS Code environment, web or desktop with the Codespaces extension. This Codespace automatically has the C++ and CMake Tools extensions installed. In my Codespace, I have quick info and autocomplete, so my C++ IntelliSense is fully working, and I can do a find all references on the numblinks variable. Now, in order to run and debug this program, it's not going to work right now. Does anyone know why? You can look at that squiggle at the top of the file. So the Raspberry Pi comes with this Wiring Pi library installed that my Ubuntu Linux container does not have. There are a few ways that I could get around this. The first is I could customize this code space to use a Raspberry Pi Docker image. I could also set up port forwarding from this code space to my Raspberry Pi, or I can run builds and tests on my Raspberry Pi in a CI/CD pipeline. I'm going to go with the third option today so that I can show you how to use GitHub Actions to level up your development and debugging workflow. So let's make a change to this file so that we can push those changes to the repository. I'm just going to add a comment that says what this numblink variable does. And then I will stage my changes, write a commit message, sync those changes, so push those changes. And I've set my CI/CD pipeline actions to trigger anytime I push changes to my repository. Let's see it in action. We can see the result of the GitHub Actions workflow in the PR overview. And we can see it says one pending check, right? And I can see more details on github.com. So here's the commit that I just clicked through, and there's that checks tab. That's where I'll see the status of my checks. So here I have my build job. And this build job, let's take a look at it. See, it's running on my Raspberry Pi. And it's using CMake Presets to configure and build my program. It's using that same command line syntax that I showed you in a previous demo. And it's also running ctest on my Raspberry Pi Blink program. Again, using that same command line syntax because I have my CMake Presets.json file in the project root. These jobs are defined in a YAML file in my project's workflow folder. So I've set this workflow up to run every time I push changes to my GitHub repository, but you can customize this on property to almost any GitHub event. Each workflow has one or more jobs. Each job has this runs on property, which specifies the environment to run your job on. The runner can either be GitHub hosted or self-hosted. GitHub offers hosted Ubuntu Linux, macOS, and Windows virtual machines to run workflows. When you use a GitHub hosted runner, machine maintenance and upgrades are taken care of for you. You can run workflows directly on the virtual machine or in a Docker container. Being able to run workflows in a Docker container from a GitHub hosted runner is helpful if you want to run your jobs on a different OS from Ubuntu, macOS, or Windows, like Raspberry Pi. But to have even more control over your runner's hardware, operating system, and software tools, you can use a self-hosted runner, which is what I did with my Raspberry Pi. To turn my Pi into a self-hosted runner, all I needed to do was run a few commands in the terminal to install and run the self-hosted runner application. Running the application sets up communication between my Pi and GitHub such that my Pi is listening for jobs. And now, whenever I or a teammate push changes to this repository, the code is built and tested on my Raspberry Pi automatically. This is helpful if your team doesn't have enough Raspberry Pis for each developer to have one in their possession. Instead, you have one or two that are set up as runners for your project's GitHub workflow. And whenever a team member pushes changes, they can verify their changes successfully built on the Pi and pass whichever tests have been specified. Let's talk about some key takeaways from that last demo. GitHub.dev and GitHub Codespaces enable you to write and commit code directly from your web browser on any device, which is a great way to save time, avoid switching context, and get a development environment up and running quickly. Something I mentioned briefly but didn't show in today's demo is the Codespaces extension for VS Code Desktop. Let's say your team decides to use a customized Codespace container as your development environment so that you can share the container configuration files with each other and connect the environment from any device on a web browser. If you prefer working on VS Code Desktop, maybe you're more comfortable there because you have certain preferred key bindings or you like the look and feel of it better, you can connect that code space from VS Code Desktop using the Codespaces extension. Another key takeaway from this first demo is that GitHub Actions makes it easy to build and test your code in CI/CD workflows. You can use GitHub hosted runners to have machine upgrades and maintenance taken care of for you, or you can use self-hosted runners for more control over the hardware and operating system, which is what I did with my Raspberry Pi. You can add self-hosted runners at various levels in the management hierarchy. There are repository level runners, which are dedicated to a single repository, which we only recommend doing this for private repositories. You can also have organization level runners that can process jobs for multiple repositories within an organization. And finally, there are enterprise level runners, which can be assigned to multiple organizations in an enterprise account. Just to recap on some of the tools that we use today to level up our debugging workflow, we looked at CMake Presets and VC Package and how you can use those together to set up a totally cross-platform, cross-editor and IDE debugging toolchain for your projects. You can use both of those with Visual Studio, with VS Code, and in both Visual Studio and VS Code, you can target platforms different from your host operating system. We also looked at how you can use GitHub Actions and GitHub Codespaces. GitHub Actions enables you to add an additional layer of error checking and bug catching to your application development workflow. And GitHub Codespaces does two things. One, it makes you more efficient if you don't like switching context between your browser and your desktop editor or IDE. And secondly, if you use Codespace configuration files, that's a very easy way for you and your coworkers to access the same clean, consistent development environment for building and debugging your program. And with GitHub Codespaces, you don't have to install any compilers, debuggers, or project dependencies locally. So it's a great way to ensure that you and your coworkers are all using the same exact development environment for build and debug and testing. Remember, our 4 recommendations today for leveling up your debugging workflow are: 1, to use CMake Presets to easily debug the same project on different platforms and in different editors and IDEs. 2, use Disassembly View to understand how data is represented in memory when you're debugging. And 3, automatically catch bugs in your program before shipping to production by setting up a CI/CD pipeline with GitHub Actions. And recommendation number 4, use GitHub Codespaces to create consistent, fast, and clean development environments accessible from your browser.